Bismillah, alhamdulillah, wassalatu wassalamu ala rasulillah. This is a review of chapter 11. Let us first review the formulas that we studied. So first we studied sequences, and we said that a sequence is convergent if it has a limit, if limit an when n goes to infinity is L, but if the limit is infinity, then the sequence is divergent. We have seen also some theorems about the sequence, convergence of a sequence, especially the squeeze theorem for sequences. If Bn is between An and Cn and limit An and limit Cn also is L, then limit Bn would be L. If we find also that the limit of the absolute value of a sequence is 0, then the limit of the sequence is 0. And we have seen that the limit of r to the power n is 0 if r is a number between -1 and 1, and is 1 if r is 1. We studied uh, the geometric series as example of series in section 11.2, and this is the form of the geometric series from 1 to infinity a times r to the power n minus 1. And we have seen that if absolute value of r is less than 1, then the sum of the geometric series is a over 1 minus r, where a is the first term and r is the common ratio. And we have taken some tests for divergence of a series. The test for divergence says if limit an does not exist or not equal to 0, then the series is divergent. The integral test, and there are certain conditions. The function has to be continuous, positive, decreasing on 1 to infinity. And if the improper integral is convergent, then the series would be convergent. And we have studied these two examples about, or these two cases about integral test. And the direct comparison test, if we have two series and we say that less than convergent is convergent, greater than divergent is divergent. And we usually compare with the p series, summation 1 over n to the power p, which is convergent if p is greater than 1, and the geometric series, which is convergent when absolute value of r is less than 1. If we cannot use the direct comparison test, we use the limit comparison test. If limit an over bn is c, where c is greater than 0, then an and bn both converges or both diverges. The alternating series test, if bn is decreasing and decreasing to 0, then the series is convergent, the alternating series. And a series is absolutely convergent if summation absolute value of an is convergent. And it is conditionally convergent if this series is divergent, while the original series summation an is convergent. The ratio test, limit absolute value of an plus 1 over an. If the limit is less than 1, absolutely convergent, greater than 1, absolutely divergent. And the root test, the nth root of absolute value of an. These are the formulas, and let us take some exercises. Determine whether the sequence is convergent or divergent. So to find out, we try to find the limit. So the limit of an when n goes to infinity. When n goes to infinity, we take the highest power, the term with the highest power. We can cancel n cube with n cube, and the limit would be half. So it is divergent. This sequence converges to half. This is another sequence. I will write it 9 times 9 to the power n over 10 to the power n. So it's 9 times 9 over 10 all to the power n. Of course, this is an. There is no summation. This is an. So the limit of an would be the limit of 9 times 9 over 10 to the power n when n goes to infinity. And this is equals 9 times the limit of 9 over 10 to the power n when n goes to infinity. And this is 9 times 0 equals to 0. Because 9 over 10 is r, and it is less than 1. So this sequence, sorry, converges to 0. I have sign n here, and sign n could be sometimes positive, sometimes negative. But I know that sign n is always between -1 and 1. So if I multiply by n, n is a positive number. It starts from 1 to infinity. And if I divide by n square plus 1, all the sides. So this is an, and it is between two sequences. I can find the limit of n over n plus 1 when n goes to infinity. We take the highest power. N cancels with the square root of with the 2, so 1 over infinity is 0. So the limit of the sequence is 0, and the limit of negative n over n squared plus 1, also the term with the highest power, same. Negative 1 over infinity is also 0. So by squeeze theorem, limit of an when n goes to infinity, where an is this one, is equal to 0. So the series converges to 0 by the squeeze theorem. Well, if I try to find the limit here, when n goes to infinity, I'll have infinity over infinity. Ln infinity is infinity. Infinity over infinity, so I need to use the function. I will deal with the function. There is a theorem. If the function has a limit, then the sequence has the same limits. Well, infinity over infinity, this means I can use L'Hopital's rule. The derivative of ln x is 1 over x. Derivative of square root of x is 1 over 2 square root of x. So this is limit 1 over x, so x will be here. And this is 1 over 2 square root of x, so it would be here. Okay. So I will have limit 2 over square root of x over x. I'll have square root of x here because 1 minus half, x to the power 1 minus half, which is half. And now 2 over infinity is 0. So the limit is 0. So limit an when n goes to infinity is also 0. So the sequence converges to 0. The sequence is convergent and it converges to 0. If I try to find the limit, 3 over infinity is 0, 1 to the power infinity. So I'll find the limit of 1 plus 3 over x to the power 4x when x goes to infinity. 1 to the power infinity. So I call y equals 1 plus 3 over x to the power 4 over 4x, and then I take len both sides. So len y would be len of this. I can bring 4x here using the properties of the logarithmic function. And now I find the limit of ln y when n goes to infinity. And the limit of ln y would be the limit of this. And now if x goes to infinity, 3 over infinity is 0, ln 1 is 0. I have infinity times 0. So infinity times 0, I need to bring one of these two below. This is how to deal with infinity times 0. So let me bring, keep the 4 up and write x 1 over x. Now if I replace x by infinity, ln 1 is 0, 1 over infinity is 0, so I'll have 0 over 0. So I can use L'Hopital's rule. The derivative of 1 over x is negative 1 over x squared. The derivative of ln 1 over 4 plus 3 over x times the derivative of 1 plus 3 over x. Derivative of 1 is 0. Derivative of 3 over x is negative 3 over x squared. So if I just multiply both sides by x squared, I can find out that the negative cancels with the negative and x squared cancels with x squared, and I'll have limit negative 12 over 1 plus 3 over x. You can cancel positive 12 because negative 1 over x squared can be cancelled with negative 1 over x squared if you like, and the 3 will be multiplied by 4, so I have 12 over 1 plus 3 over x. If I replace x by infinity now, 3 over infinity is 0, 12 over 1 is 12, so the limit is 12. So ln y goes to 12. This means that e to the power ln y, or y approaches e to the power 12. So this sequence is convergent, and it converges to e to the power 12. And now to the series, determine whether the series is convergent or divergent. And if I find the limit of an, I'll find that the limit is 0 because I'll have 1 over n squared over n cube. Okay, so what but you can also see that this is a rational function, and we deal with rational function by finding this is summation an. Okay, let me talk about bn. What is bn? N squared over n cube, or 1 over n. So I will compare summation 1 over n to this series, these two series. I cannot prove that an is greater than bn by direct comparison test because I know that this series summation 1 over n is the divergent harmonic series. So I expect that this series is also divergent, but how to prove that? I cannot use the direct comparison test, but I can use the limit comparison test. Let us find limit an over bn when n goes to infinity. And if we prove that this limit is greater than 0, then summation an would be also divergent. So this would be the limit of, this is n square plus 1 over n cube plus 1 over bn. So what times n? So I'll have, in fact, n cube here and n here. And the limit when n goes to infinity would be the limit of n cube over n cube, the highest power. So it would be 1 greater than 0. So by limit comparison test, summation an is also divergent because summation bn is divergent. Well, this is uh, an alternating series, and bn here is 1 over square root of n plus 1. And it's clear that limit bn when n goes to infinity is 0, 1 over infinity is 0, and 1 over, if I replace n by n plus 1, so I'll have n plus 2, 1 over square root of n plus 2 is in fact less than 1 over square root of n plus 1, because square root of n plus 2 is greater than square root of n plus 1. So these are the two conditions of the alternating series test. So by alternating series test, summation an is convergence. Well, if I try to find the limits of an here, when n goes to infinity, I can, the len is a continuous function, so I can take the limit inside the len, and now I deal with the highest power when n goes to infinity, so n over 3n. So the limit is 1 over 3, so it is len 1 over 3. So the limit of an is len 1 over 3. And this is not equal to 0. So series, the summation an is divergent by test for divergence. By the test for divergence. Well, I have cosine 3n over 1 plus 1.2 to the power n. Well, I know that cosine, any cosine is always between 1 and negative 1, so it's less than 1. So I can divide both sides by this one, less than or equal to. Okay, but this is 1 plus 1.2 to the power n, so I can write it like this. Okay, because the denominator is greater, so this is less than this. And now what do we know about this? 1 over 1.2 to the power n. I can write it 1 over 1.2 to the power n. And if I use the calculator 1 over 1.2, I'll find that it is 5 over 6. And 5 over 6 to the power n, this is what? Okay, what is but? Summation 5 over 6 to the power n when n goes to where from 1 to infinity is a geometric series with r equals 5 over 6 less than 1. So it is convergent. So by direct comparison test, summation an is also convergent because we proved that summation an is less than bn, and summation bn is convergent, so summation an would be convergent. This is the direct comparison test. Well, here I have n and n, so I will use the root test. So what is this? Everything is positive here. So the nth root of absolute value of an would be n square, okay, over 1 plus 2n square. If you raise this, if you take the nth root of an. So what is the limit of n square over 1 plus 2n square? When n goes to infinity, we take the highest powers, cancels, so the limit is 1 over 2. 1 over 2 is less than 1. So by the root test, summation an is absolutely convergent. This is by the root test. I have n, but I have n square here. There is no power here. So I will use the ratio test. So what is absolute value of an plus 1 over an? I'll have negative 5 over, well, let me simplify an first. Okay, this is an. I'd like to write it in an easier way because this is negative 5 to the power 2n. So I can write it negative 5 to the power 2 all to the power n. And negative 5 to the power 2 is 25. So in fact, I have 25 to the power n all to the power n square 9 to the power n. So an plus 1 would be 25 to the power n plus 1. And here I'll have n plus 1 to the power 2 and 9 to the power n plus 1. This is an plus 1 over an, which is this one. So I'll have n square times 9 to the power n over 25 to the power n. Cancellations, I'll have 25 here, 9 here. So the limit, this will go to n square. Okay, let me just write all the steps. It will be equal to n square over n plus 1 to the power 2 times 25 over 9. So the limit of absolute value of an plus 1, which is, let me write immediately, we have 25 over 9 times n square plus n plus 1 square. And the limit of this when n approaches infinity is 1, because I take the highest power here and the highest power here. So the limit is 25 over 9, and this is greater than 1. So by ratio test, summation an is divergent. If the limit is greater than 1, this here is divergence. Other types of questions determine whether the series is absolutely convergent, conditionally convergent, or divergent. So let us find out here. Well, usually we take the absolute value of an and see what would happen. This is n to the power negative 1 over 3, so I can write it 1 over n to the power 1 over 3. Well, absolute value, the negative 1 will disappear and I will have 1 over n to the power 1 over 3. And what do we know about summation 1 over uh, n to the power 1 over 3? This is a p series with p equals to 1 over 3 less than 1. And if it is less than 1, if the p series is less than 1, then it is divergent. If it's greater than 1, it is convergent. If it is less than 1, it is divergent. So it is divergent. So summation absolute value is divergent. So the series is not absolutely convergent. But let us now use the alternating series test. Bn is 1 over n to the power 1 over 3, and limit Bn when n goes to infinity is 0, and 1 over n plus 1 to the power 1 over 3 is less than 1 over n to the power 1 over 3 because n plus 1 is greater than n. So these are the two conditions of the alternating series test. So by alternating series test, summation an is convergent, but summation absolute value of an is divergent. So summation an is conditionally convergent. 25. Well, I have power n, power 2n, and n plus 1. So I'll use the ratio test. I will have negative 1 will disappear with the ratio test, so there is no need to write it. I'll have n plus 1 plus 1, so I'll have n plus 2 times 3 to the power n plus 1 over 2 times 2 times n plus 1 plus 1. That's 2n plus 2 plus 1, so it's 2n plus 3. And divided by an, I have 2 times 2n plus 1 over n plus 1 times 3 to the power n. There's no need for the absolute value. Everything is positive here because we did not write negative 1. So cancel this with this. I'll have 3. Cancel this with this. I'll have here 2 to the power 2 times 2 to the power 2n plus 1. So actually, I have 4 here. So 3 over 4 times n plus 2 over n plus 1. Well, the limit of n plus 2 over n plus 1 is 1. So this goes to 3 over 4, which is less than 1. So summation an is absolutely convergent by the ratio test. Okay. What about this one? If you notice that I have summation n over ln n. And let us try to find the limit of this. The limit when n goes to infinity is infinity over infinity. So let me see what is the limit of square root of x over ln x when x goes to infinity. Infinity over infinity, I'll use L'Hopital's rule. I have 1 over 2 square root of x here and 1 over x here. So I'll have 2 square root of x here, and I'll have the x here. And x over square root of x is square root of x, 1 minus half over 2. So the limit is infinity. Okay. So the limit of Bn is infinity. So this means that the limit of negative 1 to the power n when n goes to infinity does not exist. Okay, does not exist. It would be positive or negative infinity. So summation an is divergent by test for divergence. Okay, so summation absolute value is divergent, and summation an is also divergent. Other type of questions, find the sum of each series. When he says find the sum, so either we have a geometric series or telescoping sum. This looks like a geometric series. This starts from 1, so I need to write it. To find the sum, I need to determine the first term and r. So I'll try to write it like this. Here I have negative 3 to the power n minus 1, so that's good with me. I need it to be to the power n minus 1. But here I have 8 to the power n, and 8 to the power n, I can write it 8 times 8 to the power n minus 1. So I have summation 1 over 8 times negative 3 over 8 all to the power n minus 1. So this is written in the form which we know, the form of the geometric series, a times r to the power n minus 1. So a is 1 over 8 and r is negative 3 over 8. And it's clear that this is a convergent geometric series because absolute value of r is less than 1. So the sum is a over 1 minus r. A is 1 over 8. And here 1 minus minus, so plus 3 over 8. So it's 1 over 8 over 11 over 8. If you multiply by 8 over 8, you get 1 over 11. So the sum of the series is 1 over 11. Here we have a telescoping sum. So let me find Sn. Sn, the nth partial sum, the sum of the first n terms. So it's summation from, let us say, I to n of tan inverse I plus 1 minus tan inverse I. So I have tan inverse, if I replace I by 1, 2 minus tan inverse 1 plus tan inverse, replace I by 2 now, 2 plus 1 is 3 minus tan inverse 2 plus replace I by 3 tan inverse 4. Yes, here we replaced I by 1, here we replaced I by 2, here we replaced I by 3, and so on. Minus tan inverse 3, and continue like this. And the last terms for I minus 2, okay, n minus 2. If I replace I by n minus 2, I will have what? N minus 2 plus 1, so I'll have n minus 1 minus tan inverse n minus 2. If I replace by I by n minus 1, I'll have tan inverse n minus 1 plus 1, that's n, and here tan inverse n minus 1. And then replace I by n, so I'll have tan inverse n plus 1 minus tan inverse n. So let us cancel what we can cancel. Notice that I have here tan inverse 2, and it cancels with this one. So the first term of these two terms is cancelled. And then tan inverse 1 is not cancelled with anything. Okay. Tan inverse 3, the first term of these two terms would be cancelled here. So tan inverse 4, which is now the first term here, the next one here would be tan inverse 5 minus tan inverse 4. So the first term would be cancelled with this one. Okay, this is the first term. It would be cancelled with the second term. So always the first term of these two terms, the first term is always cancelled with the second term, starting from here. But this one is not cancelled. So at the end, I'll have negative tan inverse 1. It would be there. What about if we go from the left? Okay, I have 2, 2, 2. Start from here. Negative tan inverse n. Is it cancelled with something? Yes. So the first, I can say, let me say the first term here from the right is cancelled from this one. What about this one? This one is not cancelled with anything. So this one, the first term of these two will be cancelled with this one. So here also the first term will be cancelled with something here. And at the end, this is the telescoping sum. I will have negative tan inverse n, negative tan inverse 1. Okay, so this would be the sum. Sorry, this has been cancelled. What's not cancelled is tan inverse n plus 1. Okay, so this is Sn, and we can find now the limit of Sn when n goes to infinity. And the limit of Sn will give you the sum. Okay, so the limit of tan inverse n plus 1 when n goes to infinity, it would be tan inverse infinity. And you know the limit of tan inverse when n goes to infinity is pi over 2. And tan inverse 1 is pi over 4. So pi over 2 minus pi over 4 is pi over 4. And this is the sum of the series. So the sum of the series would be pi over 4. Express the repeating decimal as a fraction. Well, we solve this exercise by writing this as a geometric series. So this number, in fact, is equal to 4.17 plus. I have 326 repeated, 326 repeated, 326 repeated. So the first 326, I can write it 326 over what? How many decimals here? 5 decimals. So over 10 to the power 5. Plus 326, the other 326 would be 10 to the power 8 because I have 8 decimals. And then 326 over 10 to the power 11, and so on. Okay. So this is in fact a geometric series with A, the first term, is 326 over 10 to the power 5. And R, if I divide any term by the previous term, I'll get what? Let us do it. Or you can think you multiply by what? So I'm actually multiplying by 1 over 10 to the power 3. This is R. And R is less than 1. So this is a convergent geometric series. So this would be equal to, I can find the sum of this geometric series then. What is the sum? It is A, which is 326 over 10 to the power 5 over 1 minus R. And R is 1 over 10 to the power 3. Okay. And you can find this by the calculator or multiply by 10 to the power 5 up and down. So I'll have 326 over 100 minus 10 to the power 5 minus 10 to the power 2 or 100. Okay. So if I just add these two using the calculator, I will have the number 416,909 over 999 zeros. So we wrote this number as a fraction using writing these repeating decimals as a geometric series. This is the last section. Find the radius of convergence and interval of convergence of this series, power series. You remember we use the ratio test. So an plus 1 over an would be, I'll have x to the power n plus 1 over n plus 1 square times 5 to the power n plus 1 multiplied by n square 5 to the power n x to the power n. And canceling this and canceling this. And if we take the limit when n goes to infinity, n square over n plus 1 square will go to 1. So this will go to absolute value of x over 5. So this series would be absolutely convergent if absolute value of x over 5 is less than 1, which means absolute value of x is less than 5. So the radius of convergence is 5, and x is between -5 and 5. This is the interval of convergence, but I have to check the two special cases when x is 5 and -5. Let me start by -5. So I replace here x by -5. Notice that -1 to the power n, -5 to the power n, I can multiply these two and have 5 to the power n, and it will be cancelled with the 5 to the power n below. So in fact, this is equal to summation 1 over n square. And this is a convergent P series because P is 2 greater than 1. While if X is 5, I'll have summation 5 of to the power n will be cancelled with 5 to the power n, and I'll have this series. And for this series, Bn is 1 over n square, and limit of Bn when n goes to infinity is 0, and 1 over n plus 1 square is less than 1 over n square because n plus 1 square is greater than n square. So by alternating series test, summation an, okay, this series is, let me not say an, let me keep an for the original one. So this series is convergent. So the interval of convergence is -5 to 5 closed because at 5 it is convergent and at -5 it is also convergent. Uh, Similarly, x plus 2 to the power n plus 1 divided by a to the power n cancel, cancel. And if I use the limit when n goes to infinity of n over n plus 1 would be 4, would be 1. So this will go to, after taking the limit, it will approach absolute value of x plus 2, okay, over 4. So the series is absolutely convergent if absolute value of x plus 2 over 4 is less than 1, which means absolute value of x plus 2 is less than 1 times 4, which is 4. So the radius of convergence is 4, and the interval of convergence would be adding -2 to all sides. So x is between -6 and 2. And let us discuss the case when x is -6. Because if x is -6 and 2, the ratio test does not work because L would be 1. -6 plus 2 to the power n, this would be -4 to the power n. So I can write it's -4 to the power n over 4 to the power n. So I will have -1 to the power n over n. And this series is convergent by alternating series test because limit of 1 over n when n goes to infinity is 0, and 1 over n plus 1 is less than 1 over n. While when x is 2, I'll have 2 plus 2, 4 to the power n will be cancelled with 4 to the power n. So I'll have 1 over n. And 1 over n is the divergent harmonic series. So the interval of convergence is at -6 it's convergent, but at 2 it is divergent. Let us use the ratio test. n plus 1 plus 2 n plus 3. Cancellations. N plus 3 factorial is n plus 3 times n plus 2 factorial. So they cancel with each other, and here I have x minus 2. Now the limit would be when n goes to infinity of, yeah, let me write it. I will have the following: 2 over n plus 3 absolute value of x minus 2. Okay, because we don't know whether x is positive or negative. So the limit of 2 absolute value of x minus 2 over n plus 3 when n goes to infinity, anything infinity plus 3 is infinity, anything over infinity is 0. Of course, x is not infinity, and 0 is always less than 1. So the series is absolutely convergent. So it's always convergent. So the radius of convergent is infinity, and the interval of convergence is from negative infinity to infinity. Use the ratio test. N plus 1 plus 3 will give you n plus 4. Cancellations. Now limit square root of n plus 3 over square root of n plus 4 will go to 1, n over n. So this will go to 2 times absolute value of x minus 3. And this is absolutely convergent if 2 times x minus absolute value of x minus 3 is less than 1, which means absolute value of x minus 3 is less than half. So the radius of convergence is half. Okay. And the interval of convergence would be x minus 3 between negative half and half, adding 3. 3 minus half is 2.5, which is 5 over 2. 3 plus half is 7 over 2. So 5 over 2 and 7 over 2. And let us discuss the cases when x is 5 over 2 separately. If I put x 5 over 2, 5 over 2 minus 6 over 2, negative half to the power n. So I have negative half to the power n. Now I can I can write it 2 times negative half all to the power n. Combine the powers. Then 2 times half is 1. So I'll have summation negative 1 to the power n. And this series is convergent by alternating series test, because limit of this bn is 0, and 1 over square root of n plus 4 is less than 1 over square root of n plus 3. So it's convergence. While if x is 7 over 2, I'll have half to the power n times 2 to the power n. This would be 1 to the power n, which is 1, and I'll have this series. And this series, I can compare it with the series 1 over square root of n. And 1 over square root of n is divergent p series, because p is half less than 1. And I can find the limit of an over bn. Okay, well, this is an and this is bn. Using the limit comparison test when n goes to infinity. So I'll have square root of n plus 3, 1 over square root of n plus 3 times square root of n will come here. And the limit when n goes to infinity would be square root of n over square root of n, that's 1, which is greater than 0. So by by limit comparison test, summation an is also divergent. So the interval of convergence would be when x is 5 over 2, it is convergent. But when x is 7 over 2, it is not convergent. And that's the end. I hope you enjoyed studying and reviewing chapter 11.